take the raw stuff of our planet, the materials that give names to the ages, stone, bronze, iron, and more, and craft them into new forms, expanding our horizons, exploring hidden worlds, and engineering life-changing technologies. Always pushing the limits to be colder, faster, safer, wilder, and now a new era is upon us. As scientists turn for inspiration to the ultimate inventor and engineer, nature. What can we learn from living things to make our own technology even better? How long before they become self-aware and turn on their overlords? I'm David Pogue, and I'm on a quest for the world's wildest new stuff. From a carnivorous tropical plant,
Oh, little shop of words.
to an elephant's trunk, little elephant snot for you, there's a revolution underway as scientists borrow the best ideas nature has to offer
I feel like an outtake from Ghostbusters.
and put them to work, creating a robot as big as an ox
LS3, get up.
and just as sturdy on its feet,
The power!
even teaching viruses
Oh,
to make batteries.
come on!
Nature has been making stuff for billions of years. What happens when scientists open up its toolbox to make stuff wilder?
Major funding for NOVA is provided by the following. The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And the Corporation for Public Broadcasting and viewers like you, thank you. Major funding for making stuff is provided by the National Science Foundation, where discoveries begin. Additional funding is provided by the U.S. Department of Energy's Office of Science.
We humans love to invent. We've been doing it for thousands of years. But how many of our inventions really stand the test of time? Now imagine a world filled with only the very best stuff, amazing ideas, and astonishing designs. Each one the result not just of years, not of decades, but millions of years of research and testing in an environment where the competition can be ruthless. Since life began on Earth, it has been innovating, making discoveries in materials and engineering we've only recently begun to appreciate. The hard-won lessons of life on Earth, gained over eons, may help solve our very human problems. Can forms found in nature reshape our machines, making them more useful? Can we build the agile movements of animals into our robots? Have some of the best ideas for new materials already been discovered by nature? What if we could make things like nature does? Can we grow the electronics and fuels of tomorrow using the code of life itself, DNA? The search for answers to these questions has taken some strange turns. Here at the University of Guelph, about an hour outside Toronto, materials scientist Atsuko Negishi and biologist Julia Hare think that these lovely creatures, called hagfish, may revolutionize how we make strong materials.
These are Pacific hagfish. They are well known for their unique defense mechanism.
So if I wanted to see this, what would we do? Like, could we poke at it with a stick?
I think the best way to do it is to reach in there and grab one.
Oh my gosh, look at that disgusting... Oh no! I've been slimed! I feel like an outtake from Ghostbusters. Look at the quantities of this stuff! This is like 3 times the volume of the fish! How could all this slime come out of that tiny thing?
It's an impressive display of slimosity, and it works great as a defense. When a gill-breathing predator bites down on a hagfish, it gets a mouthful of slime. With its gills clogged, it becomes more worried about suffocating than eating. So how does the hagfish conjure all that slime? One of the key components is mucin, a family of proteins that includes, you guessed it, human mucus. Mucin consists of a protein backbone with lots of sugar side chains hanging off of it, like bristles on a brush. These side chains attract water molecules, soaking them up remarkably well. In fact, amazingly well. Atsuko offers to show me what a little dab of hagfish juice can do.
This is beaker seawater.
Okay.
So we're gonna try to make some slime.
It's getting a little misty.
Just gonna mix it up a little bit.
All right.
And if you could lift that out.
Look at that! Oh my gosh. That tiny dab. Hey, there's no water left. It's taken the entire thing of water with it. That little tiny pea's worth of white stuff. Would anyone like some, children? There's plenty to go around.
While the mucin sucks up the water, it's a second component that holds the slime together so I can pick it up. These threads, visible here. Both components start out inside pores along the side of the hagfish. The water-loving mucin molecules are packed into one type of specialized cell, while the threads are wound tightly in another kind of cell. When under attack, the hagfish ejects the cells, and they break open. The mucin molecules collect water molecules, while the threads, each about 6 inches long, unfurl, binding the mucin into a continuous and disgusting mass of slime. It's these spider silk-like threads that have really caught the researchers' attention. They might even serve as a model for a new kind of fiber, because they're surprisingly strong, 10 times stronger than nylon, a synthetic material made from petroleum. If we could use hagfish fabric instead, it could help reduce our dependence on oil.
So what are the steps involved in going from hagfish slime to handsome garments made of it?
So the first step would be to be able to artificially make these hagfish slime threads.
It's early days, but Atsuko has been working on a process to create her own fiber using proteins she's derived from freeze-dried hagfish thread. She mixes the proteins with formic acid and puts a few drops onto a salt solution. Then draws up the material to create her own artificial hagfish thread. So far, it doesn't test as strong as the original, but she has high hopes.
So you started with hagfish fiber, you treated it to come up with this component goop, put it back into salt water, turned it back into a piece of thread. So you started with thread, you ended with thread. Why didn't you just use the thread to begin with?
One of the reasons is because we can't farm hagfish. And so
You can't farm hagfish?
they don't currently reproduce in captivity, and so we can't have these big farms of hagfish.
I see. Plus it'd be a pain to get up at 4 in the morning to go milk the eels.
So all of this thread pulling is really in anticipation of the day Atsuko can synthesize her own hagfish proteins.
There it is. Actual thread made of actual reconstituted fish mucus. The dawn of the era of hagfish fabric. Right there.
What would that be like? Nighttime is the right time for a fabric from the deep. Hagwear. But its look don't touch. Or the surprise will be on you. Hagwear. All right, hagfish fabric may not yet be runway ready. But in the right hands, nature's innovations offer clues that can literally shape the stuff we make. Built to thrive in their environments, animal bodies offer winning designs and possible solutions to our own engineering challenges. After all, feathered wings inspired our metal ones. Sleek swimmers helped shape our boats. What other new solutions can be found by studying the forms of animals? I'm in Stuttgart, Germany at the Wilhelma Zoo. It might be the perfect place to see the future shape of technology, according to engineer Heinrich Franzek.
So when an engineer like you comes to the zoo, do you see it differently from regular visitors?
I think so, because we want to get inspired by the nature, and here in the zoo, there's so concentrated, a huge variety of animals, all optimized for their applications, and we are thinking in applications, so this is a paradise for an engineer.
Heinrich works for an automation company trying to improve one of the most important inventions of the 20th century, the robotic arm. It's been revolutionizing factories since the first one was introduced in 1961 at General Motors. But But robotic arms have some problems. Just like the one on humans, the traditional robot arm consists of rigid parts joined together, often limiting its programmable motion. They're also dangerous. Get hit by one of these, and it's lights out. So robots often end up behind protective fences, unable to work closely with humans. The German automation company Heinrich works for, Festo, decided to reinvent the robotic arm, making it more flexible and less dangerous. Heinrich leads me to the source of the inspiration, and it turns out maybe the best arm is a nose.
So why would you look at an elephant's trunk and think this would help you with automation?
As you can see, it's so flexible and transmits a lot of force and makes it much more easier to handle things. And this is our business, handling things to automate a factory or a process. It makes sense to look into nature and to get inspired by nature. And the elephant is an excellent ambassador for that.
Thanks to Sella, a 47-year-old Asian elephant, I get a little first-hand experience with what an elephant packs in its trunk.
Little elephant snot for you.
An elephant trunk is an impressive multi-tool, able to slurp up water.
Now she collects the water.
Wow.
And squirt it.
Breakfast is on.
It picks up food like a vacuum cleaner, manipulates objects, and it's strong. Sella can use her trunk to lift over 400 pounds.
No, that's my wrist. You could crush me like a bug, couldn't
Yes,
you?
yes, sir.
Here, have some more peanuts.
But the trunk's most impressive attribute is its amazing flexibility. It comes from having no bones and about 40,000 muscles arranged lengthwise and in rings. With no bones and no joints, it's about as far away from a traditional robotic arm as you can get. I head to Festo's headquarters in nearby Esslingen to see their version of the elephant trunk. They call it a bionic handling assistant.
Now this looks like a bionic handling assistant.
Yeah, you're absolutely right. This is our trunk.
Festo's version of the trunk is made of plastic, with a series of air chambers inside. Filling different parts with compressed air causes it to bend.
So if I want it to bend that way,
We need a tube with compressed air for this expansion, and then you get this bending to the other end.
so this blows up like a balloon.
Yes, for sure.
They're testing the assistant with this simple motion for use in a packaging operation.
Look at that, it tucks it in nicely. Well done, Dumbo.
But it is inherently more flexible than a conventional arm, and, just as important, far safer.
We don't have electricity, we don't have steel and iron and all these masses which could damage a person. It's a weight of 5 pounds, some valves, a little control system.
So there's really nothing here but plastic tubes and air.
Yeah.
Does it do tricks?
In this application, the tip of the trunk works by suction. But Festo has experimented with what it calls a fin gripper, inspired by fish fins. If you push on the middle of a tail fin, it doesn't curl away from you, as you might expect. It curls toward you, giving a fish much more efficient strokes. But Festo has built that principle into a gripper that curls around the object it needs to pick up, adapting to the shape.
So it looks to me like you're about to demonstrate how this might work.
Yes, we have 2 different gripping devices, one with the fish tail, and this is a traditional one the robots are using.
Okay, can I see these things close?
Sure. Same pressure, everything is equal. Now, we will see what happens. This is the old method, and this is the bioengineered method.
Okay, let the competition begin. Look at that. Traditional robot hand, shattered to smithereens, and the fishtail gripper really did its job. So you have Robot 0, Fishtail 1. You've stolen from nature and done a great job. Thank you very much. I'll edit all this out.
Combining the fin gripper with the elephant trunk produces a flexible, lightweight, and safe robotic arm, ready for all sorts of applications.
Oh,
Here it goes. Biomimicry, nowadays, it's part of the design process here at Festo. Cross-thinking. get inspired by nature and to transform these ideas into industrial applications.
May I? Thank you.
Festo's handling assistant steals its form from the elephant trunk. But Festo isn't alone in adapting designs found in nature and applying them to industry. The beak of the kingfisher bird breaks the water with very little resistance, inspiring the shape of this Japanese bullet train so it would cut efficiently through the air. The shape of the yellow boxfish provides a rigid structure and has very little drag for such a large volume. All reasons Mercedes-Benz used it for the design of a high-efficiency concept car. But making machines that look like animals is one thing. What about making machines that move like them? For thousands of years, when we've invented new forms of transportation, many have been based on a human insight not found in nature at all: the wheel. But there are plenty of places wheels can't go, even ones wearing a belt of tank tread. The inability of our machines to traverse difficult terrain has dire consequences in the battlefield and in search and rescue. But while wheeled vehicles struggle off-road, there are some creatures getting around on legs. That's had engineers wondering, what lessons can we learn from animal movement? Can we give our machines a leg up? Walking is easy for animals. Even a toddler can do it.
Excuse me, sir. Put 'em back together right
And
now.
thanks to movies, creating walking machines seems easy too. Just look at C-3PO from Star Wars.
Oh, nice to see a familiar face. Ichuta. How rude.
Or its walkers. You'd think the problem's been solved. But in real life, it's hard. One of the best-known early attempts at a walking machine is General Electric's walking truck from the 60s. It even tackled uneven terrain, but it took a human operator to decide where to place each foot, one at a time, an exhausting task. By the 70s, computer control automated the walking motion in a series of crawlers built around the world, though still driven by human operators. These kept a tripod of legs on the ground, maintaining stability at all times, a system called static balance. They moved slowly, like a walking table. But in the 1980s, a very different approach gained ground. I've traveled to Massachusetts to visit a company that builds robots based on that work. The company's founder, Mark Raybert, has been building walking robots for over 30 years. Early on, he steered away from the static balance of walking tables. To help me understand how he views animal locomotion, he invites me to take a ride on a pogo stick. It's tricky because, like all standing humans, I am top-heavy. In technical terms, an inverted pendulum.
Here's a normal pendulum, right? If you swing it,
The
it
weight's
just
at the
hangs
bottom.
down.
Yeah.
But if you put the weight at the top, what happens? If you don't do anything, it tips over. But if you move the point of support, you can keep it balanced.
If you're top-heavy, staying balanced requires keeping your base of support under your center of gravity. That's what Mark is doing by shifting the bottom of the broom as it tips. That's what I'm doing by moving around the pogo stick. And that's what all of us do all the time when we're upright. In fact, the human brain receives constant updates to maintain the body's balance. From the inner ear, where a series of fluid-filled canals send signals about the position and motion of the head. From the eyes, which send signals about the body's position relative to other objects. From internal sensors that tell us about the position of body parts relative to each other. And from external pressure sensors in the hands and feet that send signals about the source of support, for example, if you're on uneven ground. All of this information feeds into our cerebellums, which keep our top-heavy bodies from tipping over, even when we're just standing around. Without it, you would topple over. To Mark, we are less like a static table and more like a pogo stick. To focus on the problem, he built a robot that had only one springy leg. It constantly calculated where its weight needed to shift to stay upright. Very pogo stick-like. Even when he added more legs, he kept the bounce in their step and an active sense of balance. For the last few years, Mark has been applying what he's learned to solve a problem for the US military. On rough terrain, wheeled vehicles aren't much use, and soldiers often haul everything on their backs, leading to injuries and exhaustion. Mark invites me to see Boston Dynamics' solution out at a nearby park. Meet LS3, also known as Alpha Dog. It's designed specifically for rough terrain, anywhere a soldier might go on foot, and it carries 400 pounds of gear along with enough fuel for a 20-mile mission.
So Dave, in this mode, the robot's following the leader. He's got a backpack on that has some reflective stripes on it, and the vision system focuses on that, and then it records what path he takes through the terrain.
Is it modeled after a particular animal, an ox or a horse?
Not really. We take inspiration from how animals are designed, but then we have to use human engineering tools and human materials. So sometimes it stays like the animal, sometimes it departs.
I asked Mark for a tour of LS3, of course, after it's been shut off.
So this is the leg, and it's got a muscle here, or the actuator, which causes it to move. This muscle moves the knee joint. The computer is really the equivalent of a laptop-style computer. So, you know, all the balancing is done in that computer, all the speed control, all the turning. There's a laser rangefinder here that provides 3D depth information. There's a set of cameras here that look right in front of the robot and provide information about the shape of the terrain so that the feet can pick the best places to step. The legs themselves can feel the forces that are exerted at all the actuators.
Well, does it ever slip? And what if it steps on an oily leaf or something?
It slips, and frequently it corrects for those slips. So the goal is to make it so that the feet can slip and the control system recognizes that it's slipping and compensate by using the other legs.
Lots of cool tech on LS3, but my favorite feature? Voice control.
Power on, engine off, sit, get up, and get me a beer. That's a good one. I like that. LS3, get up. The power! LS3, follow tight. What a good boy! LS3, sit. LS3, power off. I think you got something here. Nice.
In a final test of LS3, Mark has it follow the leader up a steep incline. Here, you really see it actively balancing while in motion, just like me on the pogo stick, instead of moving from one stable position to another like a walking table.
And the idea that you could have it passively stabilized like a table, that doesn't really work with a moving robot. There's too much energy in the motion of the body. I believe that the only way to make these things work is to really commit to the active balance.
LS3 isn't really built for speed. It trots at about 5 miles an hour. But what would it take to make it go faster? This is the cheetah. Just like the real deal, its back flexes with each step, increasing the stride of its gallop. Right now, it's the fastest robot with legs in the world. But start looking over your shoulder for the next generation, Wildcat. It's designed to be untethered. Four-legged robots have their uses, but events like the recent Fukushima nuclear disaster have renewed interest in the human form. Radiation kept people at bay, away from all available rescue equipment, from cars to power tools to shut-off valves. But imagine if there'd been an easily controlled humanoid robot to operate them. Robotics engineers have been working on that for years. In 2009, Boston Dynamics introduced Petman, a robot that balanced itself, walked, and even did some calisthenics. Over the last few years, Petman has evolved into Atlas, which has even more mobility. Just like LS3, it actively balances itself all the time. And in this impressive demo, all by itself, it uses its arms to work its way past a hole in the floor. Today, they're tweaking its sense of balance. on 1 foot.
Looking at what tests to do here, we studied gymnasts. And when they are just about to fall off, you'll notice that they throw their arms and their legs around very violently. So we're trying to understand what techniques they're using to build a robot that can really handle rough terrain.
They've been doing this test for only a week. First, the robot goes up onto 1 foot. Then, they hit it with a 20-pound medicine ball.
If you notice there, it's swinging its arms and legs all around in kind of a clockwise fashion. And that momentum helps move the center of mass back over the feet. Not dissimilar to the way the gymnasts do it.
Now let's see some human dynamic balancing.
The robot's blind. It doesn't know the ball's coming. So we don't want you to know the ball's coming either. And so we've got a little blinder there for you so you don't see the ball coming.
Oh, great. So I don't know when the ball's coming.
That's right.
I have a feeling if your stinking hunk of silicon and hydraulics can do it, I can, of course, do it too.
That's right.
Side by side, it's hard to say who does it better. The Atlas seems more stable. But I have a few other tricks up my sleeve.
I admire your robot, sir.
Well, I admire you wearing those glasses on public television.
We'll be seeing more of this guy. Atlas is the hardware used by 7 software development teams in an international rescue robot competition. But a single sophisticated and expensive robot like Atlas is just one strategy. What about a less expensive and less complex machine, but more of them? That's the idea behind Harvard University's Robo-Bee. It would take 30 of these to equal the weight of a penny. What happens when you move beyond having just one robot, and instead have a swarm? In the future, swarms of robots operating as a team might build our skyscrapers, or map uncharted areas, or scout out victims in disasters as robotic search and rescue teams. But in order to do any of that, engineers must solve a problem nature solved eons ago. How do you get a group of individuals to work together as one? In nature, swarms often behave as if they have a collective intelligence. Whether it's fish schooling in the sea or birds flying in a flock, the members act in unison without anyone apparently in charge. Some of the achievements built out of this swarm intelligence are awe-inspiring, like this murmuration by thousands of starlings. Or these complicated towers, built several feet high by blind termites. So what can we learn from behavior in nature about creating robotic swarms? Vijay Kumar and his students at University of Pennsylvania have been wrestling with the problem. They use a fleet of hand-sized quad-rotor robots, which they've learned to manipulate with impressive control. They can play the theme from James Bond, or put on a light show. In both performances, the quad rotors are individually controlled by a central computer. But they've also built some computing power into individual robots so they can think for themselves, like figuring out how and when to fly through a tossed hoop. Now Vijay is taking the next step, developing software that will allow the bots to work together as a swarm, a team that can do more than any single flyer can. One flying bot, pretty cool. 8 flying bots, it gets a little swarm in here.
So what you see here is these robots commanded to rise into a swarm. They're asked to form patterns, 3-dimensional patterns, and then the robots figure out what point in the pattern to step into and how to coordinate with their neighbors.
Oh, so the master computer doesn't say, you, be in the corner. It's just saying, be a rectangle, be a circle, but they have to decide how to execute that?
Right.
While a central computer could control each of the 8 robots individually, telling them where to go, Vijay wants a system that scales up. And with more robots, no computer could keep up. So instead, he's taken inspiration from swarms in nature and developed 3 guiding principles. First, as much as possible, just as in nature, each robot thinks for itself. Second, each robot acts primarily on local information it gathers. The way a bird in a flying flock probably pays attention only to its immediate neighbors to know where to go. Finally, no one robot is in charge. They're all interchangeable. so that if one breaks down, the group continues. To test out those principles, VJ turns his fleet over to me and lets me experiment. The flyers know they're supposed to make a circle. As I add them one at a time, you can see it take shape. Or I can randomly pluck one out of the air, proving none is essential, and put it back somewhere else. Its neighbors adapt. Of all the possible applications, VJ sees a big future for swarms in search and rescue, and he shows me how it would work.
So imagine you have a victim. You can imagine robots wandering around looking for maybe a cell phone signal that might tell you where the victim is.
Find that, robot drones.
I'm telling these bots to move.
The numbers are the bots.
The numbers are the bots. They're all moving around.
All right, there they go. They've chosen independent routes.
In this demonstration, run by one of VJ's grad students, the robots roam the floor, measuring the strength of a signal transmitted by our lost victim's cell phone. They share their readings, creating a map.
In effect, the transmitter is saying warmer, warmer.
Cooler, cooler. But the robots know not to trust any one sensor reading too much.
The swarm of robots cut the overall search time by gathering information faster than a single robot could, leading to the rescue of our lost little guy.
Well, right now it's a lab study, but this sort of illustrates one of the directions in which we want to go, which is you take very simple robots with very simple sensors, so they're inexpensive, you put them together, and suddenly you have the benefits of these robots collaborating to do things that they individually cannot do. And that illustrates what swarm technology can really do for you.
We've seen how nature has inspired the way robots look, how they move, and even how they act in concert in swarms. But living things have also inspired engineers on a more fundamental level, the very stuff we make things out of, our materials. Many of our modern materials have taken their cues from the natural world, especially plastics. Silk, the product of worms, inspired nylon. And the search for a substitute for rubber led to the invention of polystyrene, the stuff we often call styrofoam. But natural materials also hold hidden secrets. Tiny structures invisible to the naked eye that can give them nearly magical properties, properties we can mimic. For example, the tips of microscopic hairs on the feet of wall-climbing geckos have led to the creation of material for wall-climbing robots. So the hunt is on. What other secrets might living materials reveal? I've traveled to Harvard University to meet materials scientist Joanna Eisenberg. She's taking me to see a plant with tiny structures on its surface that play a slick trick, one we might use for new materials in sticky situations.
Oh, creepy. Little shop of horrors. What is this plant?
This is a pitcher plant, carnivorous plant. It eats stuff. It eats insects.
It's called the pitcher plant for its pitcher-shaped leaves. Though when it comes to ants and other insects, these pitchers throw a mean curve. In dry weather, ants can easily walk on the lips of the pitchers using their sticky, oily feet. But in wet conditions, the ants and their oily feet get a little shop of horrors surprise. Here's how the trick works. On a dry day, the surface of the pitcher plant looks like this. No problem for the ants. But add water and it sticks to the bumpy surface, creating a slippery wet film. A slip and slide for ants.
All these insects just slide into digestive juices inside the organism.
They fall in?
They're hydroplaning inside the plant.
Cool.
To Joanna, the pitcher plant's slippery when wet strategy seemed a promising start for developing new non-stick materials, but only a start.
It evolved this structure to capture prey. It didn't evolve this structure to create these slippery materials on metals, on plastics, on glass. So this is where material scientists come. Let's design something similar.
Taking the pitcher plant as inspiration, Joanna has developed a new non-stick surface treatment, a new way to keep stuff clean. She calls it slippery, liquid-infused porous surfaces, or slips. We start with a big piece of aluminum, The right is untreated. The left has slips.
So we're gonna try putting some stuff on each half and we'll see what sticks.
And what slips?
Well done.
First step, chocolate sauce. Haven't I seen this on late night TV?
I hate getting chocolate on my aluminum.
And on slips.
Look at that, it beads right off. Now how much would you pay?
Cleaning off the chocolate with water works, but not as easily as slips.
By gosh, Phil, you didn't even need that water. It rolled right off.
But let's raise the stakes. Next up, motor oil.
Oh, Phil, you're ruining this perfectly good sheet of aluminum. That'll never come off. What? It rolls right off.
While this one leaves a stain that is not going to be removed even with washing. It's actually getting even dirtier.
And on the slip side, no contest.
Well, I can't imagine anything much worse than motor oil.
Liquid asphalt.
If we had a studio audience, they'd be going, ugh.
And on slips.
Come on. Even tar rolls off like off a duck's back.
Seriously, it's an amazing display of unstickiness. And it works in a totally different way than the current king of unsticky, Teflon. Teflon is a plastic polymer, a long chain of repeating molecules. It has a carbon backbone with fluorine atoms tightly bonded to it on the outside. The fluorine acts as a shield, preventing the normally reactive carbon from bonding with anything else, the secret of Teflon's unstickiness. But slips works in a totally different way, on the pitcher plant principle. First, Joanna adds a porous material less than 1/100 of a centimeter thick to the stuff she wants to protect, in some cases just by spraying it on. Then she adds a liquid, often an oil, that seeps in. The layer and the liquid are formulated to attract each other, keeping the liquid in place. Just like the water on the lip of the pitcher plant, the liquid creates a smooth, non-stick surface on top. Joanna believes there are lots of applications. Graffiti a problem?
Not on the side that's been treated with slips.
Slips helps prevent ice buildup by repelling water before it has time to freeze. And if ice forms, slips defrosts more quickly, which may lead to applications in refrigeration and the de-icing of planes. It's a clever use of biology as inspiration.
By inspired is more taking some clever solution and maybe reformulating it in a different way, using something different that nature doesn't use, but the design is preserved.
So slips would bear the label based on an idea by nature.
That's right.
And of course, the research continues.
Rinse. Slips. It's absolutely repellent.
Slips cleverly adapts one of nature's innovations. But increasingly, scientists have been asking a new question. Can we adapt not only the stuff nature makes, but also the way nature makes stuff? Today's manufacturing consumes vast amounts of natural resources while creating mountains of waste, some of which is toxic. Take paper. To make a ton of it, you start with almost twice as much wood and generate thousands of pounds of waste. The leather industry is even worse. 1 ton of finished leather requires over 5 tons of the raw stuff. Compare that to the natural growth of plants and animals. They take what they need to build their bodies. No blasting furnaces, no acid baths, no pounding machinery, and waste that recycles easily. What if we could recruit nature to grow the stuff we need for our technology? What if we could grow a car, or a computer, or a cell phone? Can we make our manufacturing more like nature's? MIT professor Angela Belcher may have taken the first step toward realizing that dream.
Well, I'm really interested in how nature makes materials, how organisms in the ocean have evolved to use just the elements that they're in an environment to make really exquisite materials, like this abalone shell here.
Angela first took inspiration from the abilities of the humble abalone, whose intricately structured shell is made in part out of calcium. Over the course of its life, the abalone takes calcium atoms from the ocean and slowly assembles them into its strong shell, a talent its ancestors likely developed several 100 million years ago. which made Angela ask a question. If life could learn to build a shell with calcium, could it learn to build stuff using other elements, like the ones we use for our technology? It didn't seem likely. If you look at the periodic table, life primarily uses only 6 elements, along with a smattering of others. On the other hand, our technologies, our computers, our electronics, rely heavily on elements that nature largely ignores. Angela wondered, could she coax organisms into building stuff out of our high-tech elements? Let's say a battery? Batteries have 3 components: a negatively charged electrode, a positively charged electrode, and a separator called an electrolyte. To test her idea, Angela decided to make a negative electrode by growing it. But what creature would do the growing? She sends me down to the water, promising to show me the type of organism she recruited.
I'm sorry, I did not actually manage to get any sea organisms in there.
You did. There's actually tens of millions of viruses in the sample.
Viruses? Is this one of those medical waste beaches?
No, these are viruses that are a natural part of the environment, a really important part of the ecosystem of the ocean.
It turns out that viruses are actually the most abundant organisms in the ocean. A teaspoon alone holds over 10 million of them. Viruses come in all kinds of shapes, but in some ways they're all the same. They're each a little bit of genetic material wrapped in a protective coating. Scientists have learned how to change the genetic material inside some viruses, altering their behavior, making some strains into popular and safe lab tools for research. For her work, Angela chose one of those safe lab viruses, which happens to be long and thin, a little like a pencil. This virus reproduces by latching onto a bacterium, injecting its DNA, and forcing the bacterium to produce millions of copies of the pencil-shaped virus.
I have a model with me. This is what a virus looks like?
Yeah, exactly like that. So I have a model here.
Much better one, yeah. So this is designed to stab the bacteria.
That's exactly right, like a pencil stab.
But you're going to teach it a new trick.
Right. I'm going to teach it, instead of to bind to bacteria, to grow an electronic material.
Come on! That's like saying, well, this is where I'm going to teach the rabbit to do microsurgery.
The virus normally sticks to the outside of the bacterium it targets. But what Angela wanted was for the virus to bond with little bits of metal. And yes, that is weird.
So imagine these are tiny bits of metal that's going to be part of a battery electrode. Now, this virus has not been repurposed yet, so it has no ability to bind this material. So there's no reason that it would bind these small pieces of metal.
The stickiness her virus has for a material is determined by the virus's outer coat, which in turn is built by its DNA. So Angela had to change the DNA, rearranging its A, C, G, and T building blocks to change the outer coat so metal would stick to it.
And you have the ability to modify, mutate their DNA?
That's right. We're going to go in and we're going to add DNA sequences to them, but we're going to do it, add random DNA sequences. So it's like rolling a bunch of dice.
Angela used a process called directed evolution. She randomly mixed the A, C, G, and T building blocks of DNA and inserted the bits into the virus, creating billions of variations. Then she tested them to see which viruses bonded to electrode material until she found the one that worked best.
What you get is a virus that's completely coated in that metal that makes up this battery electrode material.
Just like an abalone assembles calcium into a shell, her virus could now assemble metal into a tiny electrode. By packing together millions of the metal-coated viruses, Angela made a negative electrode large enough for a battery. She repeated the process to create a virus that assembled the positive electrode. Adding an off-the-shelf electrolyte completed her virus battery. The virus batteries can take many shapes. These are coin batteries used in electronics. And Angela has created about 100 other specialized viruses that make other products, including solar cells with improved performance, thanks to the virus inside. And specialized materials that enable chemical reactions, catalysts, that create fuels.
Is this all about making better batteries and solar cells then, or is this something bigger?
Well, I think it's something bigger. It's a new way of manufacturing materials. Use biology to come up with new ways of manufacturing materials that have improved performance.
So let's compare the old way versus the new way. old way, high temperature, piles of waste, and lots of toxic byproducts. New way, room temperature, little wasted material, and few toxic byproducts, with a goal of none. As it emerges from the lab, Angela Belcher's work holds the promise of cleaner manufacturing and a new partnership between our industrial ambitions and the best manufacturer on the planet, nature itself. Form, movement, behavior, materials, manufacturing. All ways nature has led us to seek out new solutions to our technological problems in the amazing abilities of plants, animals, and even viruses. But while biology may also hold the answers to tomorrow's challenges and the hard-won lessons of evolution, it still takes the creativity and hard work of engineers and scientists to recognize them, combining the best of both worlds. That's making stuff wilder.
On Nova's website, you can watch this and other episodes of Making Stuff. What do you know about swarming bots, slippery carnivorous plants, and other wild things? Take the Making Stuff quiz and discover more about the brave new world of bio-inspired robots. Watch original video shorts, explore in-depth reporting, and dive into interactives. Find us at pbs.org/Nova. Follow us on Facebook and Twitter.
On the next episode of Making Stuff.
Come on in, David. Standard freezer door.
How far down the temperature scale can we go?
A billionth of a degree above absolute zero.
When things get very cold, strange things start to happen.
Oh my gosh!
Can we turn our old enemy, the cold, into a force for good?
We're trying to take the emergency out of emergency medicine.
It's levitating. The future of personal transportation right here.
Making Stuff colder. Next time on Nova.
This Nova program is available on DVD and Blu-ray. To order, visit shoppbs.org or call 1-800-PLAY-PBS.
Times the volume of the fish. How could all this slime come out of that tiny thing?
It's an impressive display of slimosity, and it works great as a defense. When a gill-breathing predator bites down on a hagfish, it gets a mouthful of slime. With its gills clogged, it becomes more worried about suffocating than eating. So how does the hagfish conjure all that slime? One of the key components is mucin, a family of proteins that includes, you guessed it, human mucus. Mucin consists of a protein backbone with lots of sugar side chains hanging off of it, like bristles on a brush. These side chains attract water molecules, soaking them up remarkably well. In fact, amazingly well. Atsuko offers to show me what a little dab of hagfish juice can do.
This is beaker seawater.
Okay.
So we're going to try to make some slime.
It's getting a little misty.
Just going to mix it up a little bit.
All right.
And if you could lift that out.
Look at that! Oh my gosh. That tiny dab. Hey, there's no water left. It's taken the entire thing of water with it. That little tiny pea's worth of white stuff. Would anyone like some children? There's plenty to go around.
While the mucin sucks up the water, it's a second component that holds the slime together so I can pick it up. Take the raw stuff of our planet, the materials that give names to the ages, stone, bronze, iron, and more, and craft them into new forms. Expanding our horizons, exploring hidden worlds, and engineering life-changing technologies. Always pushing the limits to be colder, faster, safer, wilder, and now a new era is upon us. As scientists turn for inspiration to the ultimate inventor and engineer, nature. What can we learn from living things to make our own technology even better? How long before they become self-aware and turn on their overlords? I'm David Pogue, and I'm on a quest for the world's wildest new stuff. From a carnivorous tropical plant,
Little shop of words,
to an elephant's trunk,
little elephant snot for you.
There's a revolution underway as scientists borrow the best ideas nature has to offer.
I feel like an outtake from Ghostbusters.
And put them to work, creating a robot as big as an ox.
LS3, get up.
And just as sturdy on its feet.
The power
Even teaching viruses to make batteries.
Come on!
Nature has been making stuff for billions of years. What happens when scientists open up its toolbox to make stuff wilder? These threads, visible here. Both components start out inside pores along the side of the hagfish. The water-loving mucin molecules are packed into one type of specialized cell, while the threads are wound tightly in another kind of cell. When under attack, the hagfish ejects the cells, and they break open. The mucin molecules collect water molecules, while the threads, each about 6 inches long, unfurl, binding the mucin into a continuous and disgusting mass of slime. It's these spider silk-like threads that have really caught the researchers' attention. They might even serve as a model for a new kind of fiber, because they're surprisingly strong, 10 times stronger than nylon, a synthetic material made from petroleum. If we could use hagfish fabric instead, it could help reduce our dependence on oil.
So what are the steps involved in going from hagfish slime to handsome garments made of it?
So the first step would be to be able to artificially make these hagfish slime threads.
It's early days, but Atsuko has been working on a process to create her own fiber using proteins she's derived from freeze-dried hagfish thread. She mixes the proteins with formic acid and puts a few drops onto a salt solution. Then draws up the material to create her own artificial hagfish thread. So far, it doesn't test as strong as the original, but she has high hopes.
So you started with hagfish fiber, you treated it.
Major funding for NOVA is provided by the following. The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And the Corporation for Public Broadcasting and viewers like you, thank you. Major funding for making stuff is provided by the National Science Foundation, where discoveries begin. Additional funding is provided by the U.S. Department of Energy's Office of Science.
We humans love to invent. We've been doing it for thousands of years. But how many of our inventions really stand the test of time? Now imagine a world filled with only the very best stuff, amazing ideas, and astonishing designs. Each one the result not just of years, not of decades, but millions of years of research and testing, in an environment where the competition can be ruthless. Since life began on Earth, it has been innovating, making discoveries in materials and engineering we've only recently begun to appreciate. The hard-won lessons of life on Earth, gained over eons, may help solve our very human problems. Can forms found in nature reshape our machines, making them more useful? Can we build the agile movements of animals into our robots? Have some of the best ideas for new materials already been discovered by nature? What if we could make things like nature does? Can we grow the electronics and fuels of tomorrow using the code of life itself, DNA? The search for answers to these questions has taken some strange turns. Here at the University of Guelph, about an hour outside Toronto, materials scientist Atsuko Negishi and biologist Julia Hare think that these lovely creatures, called hagfish, may revolutionize how we make strong materials.
These are Pacific hagfish. They are well known for their unique defense mechanism.
So if I wanted to see this, what would we do? Like, could we poke at it with a stick?
I think the best way to do it is to reach in there and grab one.
Oh my gosh, look at that disgusting... Oh no! I've been slimed! I feel like an outtake from Ghostbusters. Look at the quantities of this stuff. This is like 3